Okay, welcome everyone to this continuation of what is tropical geometry, part 10 already. And today I will tell you about how tropical and algebraic geometry are really related. Yeah. So you don't need to know this to do either algebraic geometry or tropical geometry, but it's kind of fun. And as far as I can tell, historically, this was how tropical geometry actually was originates, right? It's not maybe not quite true. So people just saw those pictures and haven't done we're talking about the 1970s, and haven't done much geometry until much later. So kind of the tropical geometry. But essentially, this is how it started, and it's kind of very nice. I should say that I'm not 100% sure how those pictures were done in the 1970s, because the 1970s is like the time where computers were around to do pictures, but maybe not as popular as they are nowadays, so it's not quite clear. But anyway, today we can have a lot of fun pictures, and the story itself is kind of nice, and it starts with complex analysis, because everything in geometry is obvious complex analysis. So I would say all of algebraic geometry, maybe not all, but a lot of algebraic geometry is motivated from complex analysis. Turns out tropical geometry is motivated from complex analysis. There you go. So let's have a look. So it's all about these little things here. If you've never seen those before, and a lot of fun pictures you probably have, but anyway, we can just still do it anyway. So they're called amoeba, and if you go to amoeba, and we should find a Wikipedia page, I guess. And these are these types of things, yeah. So, whatever, some pictures, you all know how they look like. So these one-cell organisms. This is a good picture, yeah. So we can zoom in a little bit. And if you just stare at this middle one here, doesn't it look like a tropical line? Huh, interesting. So it looks like a tropical line. Oh, this was a bit too much zoomed in. And it turns out that we should be able to go to, let's zoom in a little bit more. Of course, we are not, strictly speaking, not interested in biology. I am very interested in biology, but I guess in this video, I'm not interested in biology. There should be amoeba in mathematics, a certain type of set. We'll see that in a second. But anyway, so those guys, and you can, as I said, you can literally already see, doesn't it look like a little bit like a tropical variety here? Something like that, maybe. I don't know, whatever. Doesn't it look like a tropical variety? Anyway, we'll come to that, of course, in a second. For now, just recall that tropically, we always turn multiplication into addition. But if you take a logarithm, that's essentially the whole point of logarithm. So logarithm turns multiplication into addition. So there should be some relation between a tropical geometry and logarithms, essentially. And yeah, we'll see how that goes. It's a lot of fun. So stay with me for, well, a little bit longer. So here is, this is now really beautiful. So let's go back to the Wikipedia one. That was the one that already showed up here. Yeah, so that's that thing. Plenty of more of those. Oh, beautiful. We come back to that in a second. And if you can look at this, this already looks like a tropical curve, doesn't it? It's a little bit of a fattened up tropical curve, but essentially it's a tropical curve. And what people studied in complex geometry, mostly complex analysis maybe, is you take a polynomial, complex, so you're doing classical complex whatever, so a complex polynomial. Of course, I'm only doing real plots, but anyway, complex variety, complex polynomial, and the set of zeros is a variety, right? And you take the log of that set, and that's the thing you see here. So this is the log of this polynomial, right? So the log of the zeros of a polynomial are, well, those amoeba type set type objects. So all of these that look like that and that and that and whatever. Yeah? So a log of a zero set of a polynomial is one of those funny sets, and it's kind of fun that it already looks like a tropical variety. And yeah, so this picture that I've stolen from the McLaren, the book here, really nice, the book I'm following, the really nice one, link is in the description. I can zoom in a little bit better, and can zoom in a bit more. So literally, this is an amoeba, and you can literally see kind of this spine, skeleton, whatever you want to call it, is our tropical variety. So that's kind of a nice relationship. So the amoeba itself, I said again, essentially the log of a variety, and the spine of that thing is our tropical, right? Skeleton, spine, whatever you want to call it. So essentially, a tropical variety is a log of a variety, if you want. Huh? This is kind of interesting. An amoeba is just, people just call it an amoeba for the obvious reason. In case that wasn't clear, because it looks like that thing. That's why people call it an amoeba. But anyway, here's the formal definition. So an amoeba is associated to a complex polynomial. You can do that in n variables if you want. We only do it in 2 because I can plot it. In 1 variable, it's a bit too boring. It's just a finite number of points. That's not all that exciting. Okay, and here's how it goes. So we have our polynomial, and you take the zeros of that polynomial, right? Ignore 0 because we want to take a log. Log of 0 is not that fantastic. So let's not do that. So ignore 0, but it doesn't really make any difference. And then take the log, right? So really just a log. Absolute value of the log, negative logs are also a bit nasty. The sign, ignore the sign. The sign really comes just from our conventions. So traditionally there was no sign, and that corresponds to using the max in tropical geometry. If you're using the min, put a sign there, forget the sign. But what's really happening is we take the log of the coordinates of the zeros of the polynomial. Yeah, here's an example. And kind of what is fun, and not quite clear at all, that the area of those, like in the two-dimensional case, the area of these pictures, let me zoom in into one of those, the area is always finite. And that's not quite clear because these tentacles, they're called tentacles, they stretch out to infinity, right? So this goes all the way to infinity, and here goes all the way to infinity, and here goes all the way to infinity. Why should that be a finite area? But it is. And essentially the reason is those tentacles, they get thin exponentially fast. They get thin very, very fast, so in the end you just have this finite area. And in the limit, so in the limit at infinity, they're really just lines. So they're really then just the spines of, they're really just, the spine is really just spot on the tropical variety. Yeah, so it's kind of very, very nice. Let me pull up this picture again. So, so in the limit, when this gets arbitrary thin, actually our tropical variety is spot on the amoeba. And here it's like really just the spine of this picture, right? So here's another amoeba. And there are plenty of those. Here's a very nice one. And you, of course, can do that in higher dimensions as well if you want. So it's really fun kind of complex analysis topic. As far as I can tell, it goes back to the 1970s-ish. Okay, so far so good. And the genius is just whenever you see something. So I just colored the background. And whenever you see something that is colored in red in this case, then it's genus 1. So here's genus 1 amoeba. And the correct way of doing this is kind of fun. So if you have never seen that before, you can take a skeleton of an image. This is just a Python built-in library, and you can just do it. So your skeleton of a horse is a tropical variety. I'm not going to do this, I'm honest math. You can just read about it if you want. It's not that exciting. But essentially, there's a well-defined process to go from a shape to its skeleton. And the skeleton, this is kind of fun observation, is actually a tropical variety, a kind of a finite version. It doesn't stretch out to infinity. But here, our little horse is a tropical variety. And when I was learned that, it's kind of the following. So there was something a long time ago, when I was young, there was an Xbox Kinect, which is this thing. Maybe we can find some nice images. It's kind of this little box, and it's supposed to track your movement. So far, so good. One was one of the first of its kind. So you just put it somewhere above your television screen or somewhere, and it tracks your movement. And the way it does that is it turns you into a tropical variety. So let me try to find a good picture here. So it skeletonizes a human. Oh, this is beautiful. It skeletonizes a human. Can we zoom in? And can I just open this? No, I don't want to verify. It just skeletonizes a human, essentially that thing, yeah. And the human now is a tropical variety. Turns out the human is a non-smooth tropical variety because we have this 4-valent vertex here, yeah. So here, around the neck, yeah. So you have the 4-valent vertex. Turns out, if you skeletonize a skeletonize horse, it is actually a smooth tropical variety. So every vertex is of degree 3. This was just a little bit of kidding, but this standard procedure, skeletonize, if you've never seen that before, absolutely brilliant. You can skeletonize your own, you can skeletonize humans, you can then track motion or something, you can skeletonize an image, and maybe if you want to do some kind of image processing, this one is certainly much cleaner, and it somehow captures everything you need to know about a horse, right? So that's skeletonize, and that's essentially what we do. So we take the log of a variety, literally the log, like in the up to some minor modifications, we take the log of a variety and skeletonize it, and that is a tropical variety. And that's like the relation between tropical and a classical algebraic geometry, tropical geometry, is a log skeletonize of classical algebraic geometry. Anyway, I hope you enjoyed this video, and I also hope to see you next time.